Okay, good morning. So we have been talking about interface reconstruction in the previous lectures. Now we will specifically talk about interface advection. Okay. So if you recall, then particularly for one-dimensional flow, interface advection we have already studied, and there we first talked about the piecewise constant upwind scheme, then piecewise linear upwind scheme, and where we found that actually slug gets diffused to multiple cells once we used these two schemes. Okay, and if you recall, then particularly for interface advection in one-dimensional flows, what we did at that time using the volume of fluid method, we took the advantage of geometry of the interface. How? First, what we did actually, based on the color function data, we obtained the normal to the interface. And then after that, what we did in that previous discussion, if you recall, we placed the line which is normal to the horizontal. Okay, so if I just give you the idea, if you have say forgotten, then this was the situation. This was the situation, and in this situation, if I see my color function data, then color function data was like this cell was entirely filled, this was entirely filled, and this was only filled half. Okay, but whenever we were going with this type of configuration, then it was not true, or advection scheme was not sufficient enough to properly propagate the interface. Okay, so at that time what we did, first based on the color function data, we estimated that normal is pointing in this direction. Once the normal was pointing in that direction, then whenever the distribution of the volume fraction we have taken, what we did, we placed this C amount of color function in such a way so that the interface is actually normal to the direction of the interface. Okay, and in this arrangement, then we took the help of some geometrical parameters and then we advected the interface. Okay, so for one-dimensional flow, we were able to advect the interface using this particular scheme with 100% accuracy. Okay, so if you see, this particular scheme is nothing but our slick, where we are using the line either parallel to vertical axis or parallel to horizontal axis. Okay, but whenever we have seen the interface reconstruction for 2D interfaces, we found that majority of the time we are using piecewise linear interface calculation, where inside a cell interface will be represented with line that is having certain slope. Okay, now what will be happening in this type of scenario? In this type of scenario, whenever the interface will be propagating, its normal is there in certain other direction. Okay, I have to see the propagation of the interface in both x as well as in y direction, and its normal is pointing somewhere else. Okay, so situation is not that simple the way we were having situation simpler for the cases of slick reconstruction. Is this point clear? So that's why today we will study the basic idea about interface advection when we have reconstructed the line using piecewise linear interface calculation. Okay, so in this one, whenever we go for typically the interface advection methods are classified into two categories. One class of methods are based on the geometry of the interface. These are called as geometrical methods, and other method is called as fluxing method. Okay, so basically what is the difference between the two? If you consider that this is your grid, and in this grid, say you have certain interface, so this is all filled, this is all filled, this is all filled, say it is having some only this much portion filled. Okay, now if I consider my method in such a way so that each of this cell is considered as certain area, and here also geometrically I am considering only this much area. Okay, now if based on the data of the velocity which is available at different places, if I interpolate the velocity at all the corner points of this polygon, then what will be happening with the progress of the time step delta t? If I advect this entire geometrical object, entire polygon on the next cells depending upon the velocity field, this type of situation is called as actually geometrical mapping. Okay, and the methods which are based on this type of process, these are called as geometrical methods. Is this point clear? So what we do, typically the area of the reference phase we map, and then we try to see how this entire area will be propagating over our fixed Eulerian grid. However, geometrically also there are large number of methods which are available for this task. Second category of method is fluxing methods. So we have already understood or talked about the fluxing methods in our previous discussions as well. So if you recall, in fluxing methods what we will be doing, for example, my interface is here. So in a two-dimensional flow, there can be some portion of the interface which can propagate to this cell because of the advection in x direction. Then some portion can propagate in vertical direction because of the advection in y direction. And even in certain scenarios, the combination of two effects can also come into play, and there can be transfer of certain certain flux in the diagonal direction. Okay, so the methods which do not consider the mapping of the complete polygon, but what these does, these calculates that how much flux is crossing across this edge in the x direction, how much flux of the reference phase. So basically we are calculating flux of reference phase. So how much flux of reference phase is crossing across the edge in the vertical direction. When this type of estimates we will be doing, and based on that we will try to advect the color function, then we will be calling these methods as nothing but fluxing methods. Is this point clear? So one simple point you need to understand, that whenever I am using the geometrical method, then I need not to solve special interface advection equation. Why? Because the complete reference phase polygon I am actually translating. Okay, and that I am translating depending upon the interpolated velocity field at the corner points of this polygon. Okay, so once the complete polygon I am translating, then what is left? Nothing is left, so I need not to separately solve the interface advection equation. On the other hand, when my interest is in calculating the amount of flux which is moving across the sides of the cell, in this scenario ultimately we need to solve the interface advection equation, because in that advection equation, once we will be discretizing it, there will be the estimates of fluxes across the boundary. Is this one clear? So one method is where geometrically we try to map the entire area, we do not solve advection equation. And second class of methods is where what we do, we basically calculate the fluxes, and these fluxes are given as input to our algebraic equation, which is nothing but our interface advection equation or color function advection equation. Okay, so that is the two different classes. However, one important point you have to consider, that majority of the time for estimation of the flux of the reference phase across the common boundaries of the cell, many times we take the advantage of geometry of the interface. So if a priori we know the geometry of the interface, then it becomes easy for us to determine that how much reference phase is actually crossing across the boundary. This simple thing you can understand from your, again, the 1D advection of the interface. So whenever we studied the 1D advection of the interface, how we took the advantage of geometry. First we defined interface in the direction normal to the interface, and after that, while calculating the fluxes, we considered that if cell has translated through u delta t, then this much portion will not cause any flux, but only this much portion will come as incoming flux to this rightward cell or outgoing flux to the leftward cell. Is this point clear? So it means when we estimated this flux, at that time we took the help of geometry for estimation of the flux. All are clear with this idea? So though we can define separate class of methods, however, particularly for fluxing methods, it is not possible to calculate the flux without the knowledge of the geometry. Okay, so these will be taking certain help from the geometry in order to properly estimate the amount of fluxes which will be moving across the boundary. Is this point clear? Now, first we will be talking about only the geometrical 1D linear mapping method. So we will talk about geometrical mapping methods only. Okay. So in this class, there are two types of methods. One is called as out of cell method and other class of method is called as onto cell method. Okay. So meaning is very clear based on the word. Out of cell method tells that how much flux of the reference phase or how much portion of the reference phase actually will be going out of the cell in other neighboring cells. Whereas in onto cell method, first we estimate the geometrical portion of the areas which are going to come to the cell under consideration in the next time step. Okay, so in one case our idea is we will be determining how much geometrical portion will be going out and these will be then translating in the next time step to the neighboring cells. And in second class onto cell methods, what we will be doing from neighboring cells, we will see that how much flux or how much their geometrical portion has to come into the actually our own cell and cell under consideration, and then we will be estimating its color function based on the total geometric portion entry. Okay, then second is, of course, when this out of cell or onto cell we are doing, you can see the title. I am talking about geometrical 1D linear mapping. So whenever we will be doing this mapping, we will be doing only in one dimensional. Okay. If we have to extend this type of methods for multiple directions, in that case what we need to do? We need to use the approach similar to that of alternate direction implicit scheme. So all of you know about ADI scheme from CFD course. Okay, so what we do in alternate direction implicit scheme, for example, in CFD the common example which we give, that is nothing but about 2D conduction equation. Okay, so if I take 2D conduction equation, del T by del X plus del T by del square T by del X square plus del square T by del Y square. If it is in the steady state, then I will be taking equal to 0, otherwise temporal term also we can take. Okay, so one important point is, if I consider both of these using the implicit approach, okay, then I will be getting some system of equations which will be having entries sparsely placed. Okay, so once we have entries somewhere randomly placed in this matrix, then solving this matrix becomes, system of equations becomes challenging. Okay, so this system of equations can be easily solved if all my entries are placed close to the principal diagonal and its adjacent cells. Okay, so there then solving this type of system of equation is very easy with the help of, what is the name of the algorithm? Gauss algorithm or tridiagonal matrix algorithm, with the help of TDMA. Okay, so if I take implicit in both the sides, then ultimately what happens, my matrix is not diagonal dominant and the solution takes huge amount of time. Okay, so in order to avoid this, what we do, first we take this direction as implicit and this direction as explicit. In this way we got a diagonal dominant matrix and we solve some intermediate values. After solving the intermediate values, we consider these to be known from the intermediate values and then we apply implicit on this particular thing, so that we again get the diagonal dominant matrix. And this is how we calculate actually value of temperature field for two-dimensional flow. Is this point clear? So I am not explaining you this in detail, but just trying to recall you, if you have, say, because majority of you have taken the course on CFT, and in CFT we do talk about alternate direction implicit scheme. So what we do there, first time we take one direction explicit, other direction implicit, and second time we take second direction explicit and first direction implicit. Okay, so this is how we go for ADI scheme, alternate direction implicit scheme. In the similar way, because my method can only do the 1D linear mapping, so what we will be doing for solving two-dimensional problem, because ultimately if I am reconstructing the interface using Click, it means my problem is a two-dimensional nature. Okay, so for solving two-dimensional problems, what we will be doing, we will be using the operator splitting. What is the meaning of operator splitting? First, we will consider that interface is only advecting in which direction? X direction. Once we have advected through the X direction, then we will be considering that now it is only advecting in which direction? Y direction. Okay, so like this we will keep on adding the sequences, and this type of thing is called as operator splitting. Okay, so where the advection in two directions is performed in sequence. Okay, now you can see whenever we talk about the ADI schemes, in ADI schemes we study the concept of sweep direction. What do you mean by sweep direction? So say this is my 2D situation. If for estimating the propagation of field within the cell, if one side I am starting from calculation this direction, then in next step I will be starting calculation from the other direction, so that the effect of all the boundaries is simultaneously propagating. In the similar way, in first step, if we performed advection in X direction and then in Y direction, in next step we will first perform advection in Y direction and then in the X direction. Okay, so the way we do sweep direction in case of alternate direction implicit schemes, in the similar way we have to also employ the concept of sweeping the directions or sweeping the advection direction whenever we are using operator splitting for interface advection. Okay, so that is what is written over here. To avoid asymmetries, first motion is considered along the X direction and then along the Y direction on odd time steps, and vice versa on even time steps. Okay, so on, it means on alternate time steps we are changing the direction of the advection simultaneously. Is this point clear? Then third point is for 3D Cartesian grid. If this method I have to employ on 3D Cartesian grid, what will be happening? I will be having X, Y and Z. Okay, so it means 3 1D sweeps are required, and here we have to choose for more complex sequence of sweep directions. And typically the judgment of which sweep direction is to be chosen is typically taken based on the experience, that which one is actually serving well in terms of mass and volume conservation and in terms of actually defining the proper interfaces. Okay, so that is required in order to decide that which sweep direction we have to choose. Okay, now let's talk about one method which is out of cell explicit linear mapping. Okay, so in this method what is done, the reconstructed interface at time step n is mapped on the interface at time step n plus 1 by linearized velocity field. Okay, and each endpoint of the interface segment is moved with an interpolated velocity. What is the meaning? It is very simple. Say say this is my interface. Okay, So it is having how many, this particular line segment is how many endpoints? 2 endpoints. Now, if you consider that this is your cell I comma j, because we are working in 2 dimensions. Okay. So typically for I and j cell, I must be knowing the velocity at point I minus 1 comma j. Sorry, I minus 1 by 2 comma j, because this point will be I minus 1 comma j. So this will be I minus 1 by 2 comma j. Similarly, this will be I plus 1 by 2 comma j. Okay. Now this line segment is in such a way so that it is just both the points are lying on the interface, on the edges itself where velocities are known. But we can have some scenario if my interface line segment is something like this. Here what will be happening? I know the velocity at this point, which is ui minus 1 by 2 comma j, and at this point which is ui plus 1 by 2 comma j. But if I have to translate this line segment in the x direction, I must know the x velocity at this point and this point. Okay. So for estimating the interface velocity at these 2 points, what I will be doing? I will be applying linear interpolation. Is this point clear? So using the process of linear interpolation, first I will be calculating the velocities at the corner points of the line segments representing the interface. Is this point clear? After this, once we know these velocities, we will try to apply the approach identical to that of Lagrangian approach we use for particle transport. Okay. What we do in Lagrangian approach for particle transport? Please tell me. U can be simply written in terms of dx by dt. Okay. So if I have to estimate the particle position at time t plus 1, then x at n plus 1 will be equal to xn plus u times delta t. This point is clear? So in the similar way, if I know the velocities at line segments, then I can see what will be the next position of the line segment points. So that next position of line segment point x of tn plus 1 will be equal to x of tn plus u times, which is a function of x of tn into tn plus 1 minus t. All are clear with this point? And one important point you have to keep in mind, when we are calculating the position at time level n plus 1, we are using the velocity at time level n. It means we know already this velocity, so it will be explicitly giving me the position of nu x in the next time step. All are clear with this point? So this is an explicit equation. Okay, so this equation can be non-dimensionalized in one way. So what I can do, if I consider that my grid is uniform of size h in both the directions, okay, then what I can do, I can non-dimensionalize the position x with h. So x dash I have defined as new position, which will be equal to nothing but, sorry, x dash I have defined a non-dimensional position. What is x dash? It's a non-dimensional position, okay, which will be equal to x divided by h. And in the similar way, I have defined delta t equal to t at n plus 1 minus t of n. This is my delta t, and time also I have defined another t dash variable, which is equal to t divided by delta t. All are clear with this point? And in the similar way, I have defined non-dimensional velocity field. How I have defined? U dash is nothing but equal to u into delta t divided by h. Okay. So what is u delta t? U delta t is nothing but x It will be representing that how much this point has moved, that distance is actually u delta t. Okay, so once I have divided it with h, then it is representing the non-dimensional distance movement. Okay, so ultimately u dash is nothing but representing my the dimensionless area or dimensionless width which is moving in linear direction. All are clear with this point? So now if I employ all these non-dimensional things in this equation, what I will be getting? I will be dividing this by h, this by h, this t divided by delta t, and for u I will be using u delta t by h. So ultimately what I will be getting? I will be getting that x dash at t dash n plus 1 will be equal to x dash at t dash n plus u dash at x dash comma t dash n. This will be my equation, the same equation, but in which form? In dimensional. Okay. However, putting dash every time makes this equation bit complex, because already we have some superscripts in the form of time level. So that's why in further discussion this dash is actually avoided from the equation. So it is simply written in terms of xtn plus 1 equal to xtn plus u x comma tn. But you have to understand that all these x and u, what are these? These are the dimensionless or normalized quantities. Okay, where x is normalized with h, t is normalized with delta t, and this u is nothing but u delta t divided by h. All of you agree to this point? Okay. Now, what I need to do, I need to calculate this u x t n. Okay, how to calculate UXTN? I already told you that we need to calculate UXTN using the linear interpolation. Okay, so now you will be understanding why we have done this non-dimensionalization. What is the purpose of non-dimensionalization over here? So if you recall, in earlier discussion here which I explained, I know velocity at this point and this point, and I need to interpolate the velocity somewhere in between. Okay, if your x coordinate is being measured from the global origin, in that case you have to every time keep a count of x. But if you define some local dimensionless coordinate system which is defined with reference to the cell, in this way what will be happening, once I have scaled it with h, the left boundary will be becoming 0 and right boundary will be becoming 1 for the x. All are clear with this point? Okay, because I am dividing x by h, so if I measure any value of x with reference to this left boundary, that will be becoming 0, and at right boundary that x will be of the size h, and ultimately it will be becoming equal to 1. Okay, so as it is varying from 0 to 1, so if I have any point between 0 to in between 0 to 1, then interpolation of the velocity will be becoming easy. Is this point clear? And what will be the value of interpolated velocity? Here you can see u of x is nothing but equal to u at time I minus 1 by 2 comma j into 1 minus x plus ui 1 plus 1 by 2 comma j into x. Is it clear? And you have to remember this x is again nothing but the dimensionless position. Okay, so when x is 0, what it means? I am pointing on this face. If I am pointing on this face, then velocity should be I minus 1 by 2 comma j. So when x is 0, velocity is I minus 1 by 2 comma j. And when x is 1, I am pointing on the right face, velocity is I plus 1 by 2 comma j. All are clear with this idea? So the non-dimensionalization has helped us in defining the simple equation for linear interpolation of the velocity field. Is this one clear? Okay. Now, what will be happening? If I know u of x, what I can do? I can substitute this u of x over here. Okay, I can substitute this u of x over here and I can calculate the position at new time level n plus 1. All are clear with this idea? Okay, so this u of x I can substitute here and I can calculate the value of x at n plus 1. So that is what I have written over here now. So basically this x dash is nothing but value of x at time level n plus 1 and value of y at time level n plus 1. So one simple point, through this equation we are only advecting in which direction? Please tell me, through this equation we are advecting in which direction? Only in x direction. So that's why position in y direction will be remaining same. But the position in x direction will be equal to b times x plus ui minus 1 by 2 comma j, where my b is equal to 1 plus ui plus 1 by 2 comma j minus ui minus 1 by 2 comma j. All are clear with this point? You have to understand one simple thing. If you say that this is your cell and after advection it can either enlarge or it can either, what can happen? Second thing, it can contract as well. It can contract as well. Okay, it can either enlarge or it can contract depending upon the value of the velocity field. Okay, so it means that this factor b over here is the multiplying factor which will be controlling by how much amount the control volume or the area of the reference phase will be either expanding or it will be contracting. All are clear with this point or not? What I am saying is, if say this much was the area, if this velocity is large and this velocity is less, then it can enlarge, and while it is enlarging the slope has to be adjusted in such a way so that area is same. If this velocity field is small and this is large, in that case it will contract, it will compress. Okay, so the rate by which area either will be expanding or it will be compressing, that multiplying factor is nothing but my b. All are clear with this point or not? See, it's a very simple point. If your velocities in both the edges are same, then it will be simply translating without any change in its volume or area for a 2D case. But if velocity at this point is less and at this point is more, then it will be expanding, its area will be increasing. By what factor area will be increasing? That is this factor. Okay, because this ui minus 1 plus 2 I minus 1 by 2 comma j, it is the reference velocity relative to which this v factor is actually calculated. Okay, so this will be the factor by which it will be expanding, and in the similar way, if I consider that this velocity is large and this is small, then it will be contracting, and this b factor will be representing the multiplying factor by which area will be contracted. All are clear with this point? So now let's try to understand this with the help of some geometrical representation. Okay, so what I said that x dash, which is nothing but representing position at level n plus 1, it is equal to TXE x. What is this TXE? This is some vector which represents the transformation of the x into x dash. Okay, so basically these two components are nothing but the components of this TXE vector, where it represents the Tx means transformation in x direction and E means explicit. All are clear with this point? One important thing we have understood, that once I will be applying the transformation, either my area will be expanding or it will be contracting. All of you have agreed to this point. Now, let us consider that when I was having normal grid of side H, corresponding to that, the cell which is under consideration, that cell is having area sigma. This sigma is representing the area of the reference phase in this cell. All are clear with this point? Okay, this is the area of the reference phase in this particular cell. Now, if I apply this transformation, then what will be happening? Please tell me. If I apply the transformation on this area, then I will be having either increased area or decreased area. Let me consider that this increased or decreased area is given by gamma x. All are clear with this point? So, sigma was the area of the reference phase in the cell which is under consideration. Once I applied the transformation on this, then whatever the new area I have got, that I am calling as gamma x. All are clear with this point? Okay, now you see, this was the area sigma, and in this particular cell, the velocity field was acting in such a way so that this velocity is in the inward side and this velocity is also in the inward side. However, this arrow is longer, so it means the magnitude of this velocity is more in comparison to this velocity. All are clear with this point? So once this has contracted, what will be happening? In this scenario, whatever the central area is there, its contraction will happen. Okay. So once I applied this transformation TXE, what I have got, this much area has now reduced to this new area, gamma x. All are clear with this point? And this gamma x I am simply calling as, say, shaded area E. Okay. What is this U? If you recall, now U I need to consider in which form? Dimensionless form. And in dimensionless form, U represents U delta T divided by H. What is U delta T? This portion, how much it is translating inside this, that is my U delta T. Okay. So ultimately, U delta T will be representing this portion. This is the portion U delta T. So once this cell has compressed, then this much portion of U delta T has entered into the cell. All are clear with this point? So if this much portion has entered into the cell, now you can see that this D is the portion which has entered from left side. In the similar way, right side also I have compression velocity. So because of this compression velocity, some amount will be entering to the cell, and the amount which is entering to the cell, that is my amount F. All are clear with this point? Now, if I know that this was my original grid, on this original grid, this gamma x is the area which has contracted. So it means it is area E. And D and F represents the fraction of the areas of reference phase which has come into the cell I from the neighboring cells. Is this point clear? So these two areas has nothing but come from where? These have come from the neighboring cells. Okay. So what will be new volume fraction Cij of this? What will be the new volume fraction of this? New volume fraction of this cell will be this area plus this area plus this area. So new volume fraction of this cell will be Cij n plus 1 is equal to D plus E plus F, where D can simply be obtained from this transformation. D you can simply obtain from this transformation, and non-dimensional velocity field ui minus 1 by 2 comma j will be simply giving you this area D, and F area you will be getting from ui plus 1 by 2 comma j. Okay, so D is u I minus 1 by 2 comma j, F is u I plus 1 by 2 comma j, and E is nothing but gamma x, which can be simply obtained from the transformation. All are agreeing to this point or not? So now you can see that you have not solved any equation, but geometrically, by just mapping the polygon, whether it will be expanding or contracting depending upon the velocity field, and how much will be the fluxes based on the non-dimensional velocities, you have simply estimated the new volume fraction of this particular cell. Okay, after you obtain this new volume fraction, your interface will not be this type of zigzag. If you keep your interface this type of zigzag, it will be giving you huge irregularities. So after this, what will be our next step? After this, our next step will be to, we have got the new value of Cij at n plus 1. Now using this new value of Cij at n plus 1, I will be applying the interface reconstruction algorithm, which I have explained you in the previous lectures. And I will be getting some new line which will be representing interface for this entire cell. All are clear with this point? And once that step is done, then once again we need to advect. Is this point clear? One important point, you can see that if say this line, which is a light colored line, or I can say a thin line. So this is a thin line over here, and this over here is thick line. So let us consider that all the thin lines over here are nothing but representing the original fixed grid. That is original fixed grid. And this thick black colored line are the translated grids gamma x. Okay, so these are nothing but the mapped cells gamma x. If you consider that your velocity field is having velocity value so that flow is taking place from right to left. In this scenario, what will be happening? Your entire this right grid, which is a thick solid line, which is represented by thick solid line, that entire grid will be actually translating in which direction? Rightward direction. Okay, and while it is translating in rightward direction, you can see the thin lines will also be coming over here, and these thin lines will be representing the portions of the velocity which are portions of the reference phase which has moved across the boundary of the fixed grid. Okay, so whenever you will be working with this type of arrangement, you will never be having any empty spaces. Okay, if this area is your say D, then in between area will be E, and this area will be immediately become F. So you will not be having any discontinuity while we will be mapping the area of the reference phase using this particular scheme. Is this one clear? In the similar way, you can understand that whenever flow is parallelly to the right hand side, so again I am having some structure without any gap. But whenever I am having flow like this, then also you can see we will not be having any gap, because here this is D, this is E, this is F, but whatever this F portion is there, for central cell this entire is becoming E, and this is becoming D, and this is becoming F, which are with negative signs. Okay. So ultimately you will be finding that there will be no gap in between the areas. So in this way, whenever we will be doing the mapping, one of the advantage of this mapping is on one dimensional advection situations, when we apply this, it gives me complete area conservation. Okay. However, whenever we extend it for the multiple dimensions, in that scenario we will not be able to achieve mass conservation out of this scheme. Okay. Now, if this linear mapping scheme, I try to give you the algorithm, then what is the algorithm? In first step, what we do, we reconstruct the interface by using interface algorithm from the previous value of the volume fraction. Then we perform the advection first along x-axis by using mapping TXE to move the two interface endpoints in each cut cell. You have to remember that this thing we are only performing to the cells which are actually nearby interface. Okay, this process is not performed on the entire simulation domain. So it is only done for the cut cells. Then from updated position of endpoints, we compute the area, and of course the expression of area I have given you in the previous lecture. Okay, so if you recall, the expression of the area was given in terms of slopes or so. Okay, so using that expression I can calculate the new area, what is area D, what is area E, etc. And then we can calculate the new value of volume fraction field as dx plus ex plus fx. And then we can again the reconstruct interface from restart from C star. Why I am calling this C star? Because I am trying to extend this algorithm for two dimensional situation. Okay, so that's why I will be again reconstructing the new values of the volume fraction, and with this new volume fraction and reconstructed interface, then I will be advecting in which direction? Y direction. So I will perform advection along y axis by using mapping TYE to compute in a similar way Cij at n plus 1 equal to dy plus ey plus f. Okay. So in a single time step delta t, two times we are actually operating. First time we are operating in x direction through distance u delta t, and based on that whatever the new volume fractions we are getting, we are only calling these as C star. We are not calling Cn plus 1, because the final volume fraction should be the combined effect of the advection in x and y direction. Okay, so that's why based on restar, in between again we are reconstructing the interface, and then we are advecting in which direction? Y direction. All are clear with this point? And once we advected in y direction, then my both the advection in both the direction is completed. So whatever volume fraction I will be getting, I can calculate it the final value of the volume fraction. Okay. So in this process, you can see that nowhere we have solved any equation for advection of the color function. We have only mapped the area of the color function, and that area only we are trying to map from one cell to the next cell. Is this one clear? So maybe further I will discuss in the next class.